why we need to have multiple tendons per finger. And the thing is that for 30 some years we've been building hands. We think intuitively about using grasping with Coulomb friction, and so optimizing the grasp is all about controlling normal forces at the contacts, thereby controlling the friction force, because the tangential force is the coefficient of friction times the normal force. That's not true with adhesives. Instead, what you want to do, and this is covered in the paper, and Wilson can explain why, what you really want to do is not optimize normal contact forces, but rather try to make the contacts be along the midpoint of each phalange, thereby maximizing not the friction force, but the contact area.
In this podcast, I'm sharing my passion and curiosity for soft robotics, where we share inspiring stories about the work we do and how we can push the limit. I am Dane, and this is Soft Robotics Podcast. Support for this show comes from Science Robotics Journal. I really find Science Robotics to be a great resource for reliable and tangible research where we can really push the limit of the science we do in robotics. Great way to stay up to date with the published article is checking out the released monthly issue. All the links will be included in each episode description. We will also happen to have a regular conversation on the most published science robotic articles, where also you can contribute with your question and thoughts about the research. Thanks Science Robotics for sponsoring Soft Robotics Podcast.
Here's to ask Mark, what are the challenges mainly in adhesive, Gecko-Inspired adhesive that you think maybe if you can just tell the audience at the beginning, what are the many challenges and why do you think incorporating with anthropomorphic hand would make a difference? If you get to this more at the beginning, the problem or the challenges of Gecko-Inspired adhesion.
Yeah. So first, let me say that we've been working on Gecko-Inspired adhesives for about 15 years. It started with projects in collaboration with biologists who study the gecko, and the objective was to make something that would climb a vertical surface, such as a window or a wall. And we learned that one of the interesting properties of the gecko adhesive is that it's very directional, by which I mean that most of the time it's not sticky. It only sticks if you pull in a certain direction, which happens to be the direction that a gecko loads it when climbing up a wall. So we built these Gecko-inspired adhesives, and we used them initially for climbing robots, and then we started to look around for other applications. One of the first that we encountered was with NASA, that we realized that these gecko adhesives, if you could load them in the right way, could be useful for grasping objects in space, because you could come up very gently, contact an object, and then lock onto it without worrying about pushing it away. But that's a rather specialized application. We also had it in the back of our minds that we would like to use these adhesives for more conventional grasping applications, what you would do with an anthropomorphic multi-figured hand. And the problem there is how do you set things up so that you really get the advantage of the adhesive? In other words, how do you set things up so that the adhesive works demonstrably better than what you would get just from using soft rubber? And what makes it challenging is that, once again, you have to load these adhesives in just the right way. Otherwise, they don't stick. So what this paper is about is how to design hands such that they do load the adhesives, take advantage of the extra security that adhesion affords, and use it for grasping and manipulation.
Mm-hmm. Awesome. So maybe if we go to step of that, maybe the design process, what you mentioned, if we can break it down, the process, maybe if we go to Dane and Wilson, can you tell us more about the rule that you do that, this kind of design thinking to reach the problem?
Cool. Yeah. So just to kind of launch into that, I think one of the biggest starter kind of problems that we were trying to overcome is that when people had used these gecko adhesives in like pure grasping in a single direction in the past, there have been several different ways to try and get that really careful force loading that Mark had been talking about. But they usually relied on relatively complex transmission mechanisms or tendon networks or things of that nature that work if you just have two pads going together. But as you start to up the complexity of your hand, it becomes much more difficult to really do all this extra tendon routing on top of doing whatever actuation you're doing to actually move the hand and manipulate the grasp and whatnot. So we set out to try and find what is ideally a passive structure that we can put behind the gecko adhesives that give them this same load sharing behavior without us having to like really intentionally control it from like a high level controls perspective. And then at the same time, we also, for most of these kinds of applications, and this can be seen in some of the other hands I designed before, is just you get a lot of implicit benefit out of having more compliant grasp surfaces in the first place, because that gives you more contact area right out of the gate. And these gecko adhesives rely on contact area, not normal force, to kind of have their effect. And so the design specs there become, how do you make a compliant, like kind of squishy substance that you can put behind the gecko adhesives that give you that extra contact area, allow you to passively adapt to the shape of an object, and then passively provide this shear load sharing effect that we write about a lot in the paper and is super important to using gecko adhesives efficiently.
One thing which might be worth bringing out is like, if people are asking themselves, like, why can't you just put foam rubber behind the gecko adhesive?
Right. Yeah. And to get to that is that no matter what you're doing, when you're grabbing something, you're having there are slight irregularities in, kind of how much displacement you have before you fully engage with the surface. And effectively, it's just, if it's not a perfect plate, there's going to be some irregularity there. And which that means is that some finger pads are going to exert more force, or not necessarily more force, but are going to undergo a different loading scenario than other finger pads. But you want both of those finger pads to undergo the same amount of total force. And that's what our passive structures achieve through this diagonal buckling beam bending effect. And at the same time, they provide that extra compliance.
Maybe, I don't know if Dan would like to add something here in design, or before going... You would like to add something here?
Sure. I guess this is maybe a little bit lower level details and less of kind of the scheme of our lab working on gecko adhesives throughout the years. But on this specific project, we knew we had some of these design goals of having something that could give us a lot of contact area, but give us the kind of force loading situation that we were looking for. And so we started by having structures that were more complex or less complex even than these ribbed structures. We kind of started really broad and tried to explore a whole bunch of different ideas. And then we inevitably failed on a lot of those ideas and were mildly successful on a lot of them. And then, chose the ones that we thought were most promising from there, and then kind of continued to iterate on that, to start figuring out, more specific details like the thickness of the ribs and the height of the pad and things like that. So that was a lot of the actual work and time that we put in was thoughts on how to make kind of small changes to kind of narrow down the design that we wanted to get in the end.
Yeah. And some of those small changes have really big effects, and that like we didn't even start knowing like which direction the ribs should even be angled per se, like not like to the 1 or 2 degrees, but just like fundamentally should it be like angled left or angled right, so to speak, or if we even needed ribs in the first place, or should it be an X pattern or whatever. Like there was just a lot of that, and so to go through all that over time with this iteration process was a fun time.
This is a good point. Maybe we'll ask Mark in that case about. There's many question here. Maybe the first thing about multi-material, because I think, or multi-structures, you mentioned passive and the Gecko-Inspired adhesion here. So how do you see the combination? Maybe if you can tell us about the challenges of design perspective, like the morphology or what kind of right structure. Can you tell us more about the multi-material combination, passive and the Gecko-Inspired adhesion here?
Yeah, there's a couple of directions one can come at it. First of all, if you do look at the foot of the gecko, it, of course, is a multi-material structure. It has bones, It has the setae, which are of a fairly stiff material, keratin. But then they also have tendons, which are very flexible and are used to load the toe. And finally, they have a cavity, a sinus, if you will, with fluid to help get a more uniform pressure distribution. So it's a very, of course, complicated, multi-material, multifunctional structure. Well, that suggests that you might need something like that if you're going to try to do general grasping with adhesion in robotics. So if you look at the hand, sure, there are links which are relatively stiff, and they need to be, because you need to transform torque, which you generate with tendons and motors out to the fingers. But then we have these very compliant rib structures. But then the adhesive itself is on a very thin film, which is very flexible, but essentially inextensible. Certainly, at least in comparison to the ribs. And that turns out to be very important. That's part of this, what it's a part of is this combination of effects that gives us what we call load sharing. And what I mean by that is that what you want is that if a certain part of a finger is making contact with an object and you load it, there will be some shear stress there. And you want that shear stress to be as nearly similar as possible to what it is at other contacts elsewhere around the hand. What you absolutely do not want are local stress concentrations that would cause localized failure and peeling, and then the whole thing just kind of fails like an avalanche, and you don't get the benefits.
That's a very interesting point. Maybe based on that, maybe asking Wilson and Dan here, do you think the design, I don't know if in the paper was, you think intuitive design, or what approaches to that you can achieve and avoiding local stress at certain point of failure? It's very interesting.
Yeah, I think it stems from a kind of a fundamental stress strain curve, which is when a material is hyperelastic. It means that when you stretch it a little bit, it'll exert some amount of force like a regular spring. But then it'll hit some plateau point where you can keep stretching it, and the amount of force that it exerts back stays the same for some period of displacement. And then maybe at the end it starts getting stiffer again. But you get this flat point where it's effectively not getting any higher force for that displacement range. And there's a lot of different ways where you can achieve a force curve like that. One of the ways that people have done it in the past is with nitinol, which is just a material itself that is hyperelastic. It has that behavior kind of intrinsically. But another thing that has this behavior is if you have a beam and it is buckling, the way that structures buckle, particularly if they don't catastrophically buckle because it's rubber and it can actually bounce back, is they go through this range of motion where you get a similar kind of plateaued stress strain curve. And so we kind of knew that this very high level behavior is something that can be achieved with a structure that looks like that. But we had to really carefully tune that little plateau region to be right in the force zone that we want and occur with the right amount of displacement that we want, blah, blah, blah. So it's starting with this really high level behavior that is perhaps unique, but still interesting. And then going from there to just turn it into an actual, effective material is where all those like micro iterations come in as well.
Mm-hmm. Dane, you would like to add something here?
Sure. I think everything that Wilson said was totally on point. One thing that I'd like to add that I think is kind of especially fun about the solution that we came up with is that we're able to get this degressive stress strain profile that can, evenly distribute shear loads across an entire hand. And we were able to do that in a very local way. So we were able to do it just in this small, centimeter thick pad, and we didn't need to really connect the pads in any way for it to work. They kind of worked independently of each other. And so that's kind of just feels like a fun element of how that approach worked.
Great. So I'm curious to ask you, Mark, I want to ask you, Mark, based on that, do you think to exhibit this behavior, which one is significant to you, the structure or the material? If we speak about the design here, the structure or the material?
I think it's hard to separate that question. When we design, we tend to think about, well, what is the behavior we want? And You look at the equations that are responsible for describing the behavior and parameters both relating to the material, for example, like Young's modulus or damping, and then other parameters relating to the structure are involved. So we very much tend to consider them together. Now, that said, it is also the case that, for example, we think the rib designs are very important. We made the particular ribs on the prototype that we built out of a urethane. Could we have used something else? Well, yes, we could. We could have used some other moderately stiff elastomer, and it should have worked more or less equally well. But I actually don't separate that question from questions like, well, could I have made the ribs a little bit thinner or a little bit thicker? Yes, but then I would have had to change the material properties accordingly. So it's a coupled question.
And I'm curious also in this design process, do you have moments of doubting the approach, or maybe, I don't know if you agree or disagree, and sometimes we have this design, and do you have this moment, if you can't share it, maybe the moment you agree or disagree? I don't know if you have it in this design.
Times that things didn't work as well as Dane and Wilson imagined. Maybe you can dredge up some memories.
I mean, I don't think there were that many times where we fundamentally disagreed as a team. I think it was more of just trying to figure out what directions to go when we still had very incomplete information. Hold on. Well, I think in the beginning there was... Oh, yeah, you go.
Thank you. I think one thing that comes to mind for me is we actually had this idea of doing some sort of rib structure relatively early on. And as Wilson said, we weren't sure, which way it should angle and things like that. And we had something that worked kind of okay, and we were trying to improve it so it would actually, work significantly well on a hand. And I think we started taking an approach of kind of changing high-level features about the pads, like whether they're actually connected at the top surface or whether they're, an X shape or pretty high level things. And we couldn't get anything to work better. And so we kind of in some ways that felt like, we weren't succeeding. And then eventually we went back to what we had done before and made some kind of small level changes, like the relative thickness between the ribs and the top layer, and we were actually able to get significantly better results. So that's actually something that I like about the paper is that we try to, and this actually even ties back to the question about material, but we try to present this design process for the ribs in such a way that it could apply to lots of different scenarios. And you could even use a different material. You could have a different force range. You could have different areas that you want to apply this to, and you hopefully would be able to step through the process and change different parameters like the angle of the ribs and the thickness of the ribs to achieve kind of a similar result that we got.
Yeah, and related to that, even dealing with that, which direction do we angle the ribs in the first place, is we actually got some significant pushback from the lab in one of our earlier prototypes that we should actually really have the ribs angled the other way. Because there are some reasons why that might hypothetically be effective, but we just kept kind of trying out different things within what seemed reasonable. And as Dane pointed out, it just kind of emerged that this earlier prototype, high level geometry, was just kind of clearly had more advantages than other things. We kept going with it, and then we got it to the point where it started to have these significant greater advantages, and then it became more clear.
Great. So I'd like to go again about designing the gripper, I think, about being beyond pick and replace. And I want from you to elaborate more. Maybe Mark, if you can elaborate more, what do you mean about beyond pick and replace? Because I think already Wilson mentioned at the beginning, but if you can break it more in detail, what are the feature, what are functionality behind this design in particular?
I'll start, but I think Wilson also has some nice things to say about this. For all that people have been developing sophisticated multi-fingered hands for over 30 years, when you look in industry at what's actually used, it's simple parallel jaw grippers for the most part, because they're reliable, because they can grip firmly and precisely. So we had already done some work on, well, how would you specialize gecko adhesives for a simple parallel jaw gripper? In fact, that was one of Wilson's first papers. And that was much simpler because the loading conditions were much more consistent. It was much easier to say, all right, look, here's what we need in order to optimize the use of the adhesive. Here's exactly how we'll put the adhesive on the parallel jaw gripper to achieve that goal. But there are many applications also where a simple parallel jaw gripper will not suffice. If you would think, for example, of agriculture where you want to pick fruit from a tree, or medical applications, or robots in the home that have to grasp a wide range of different shapes and do it gently. These are all the kinds of applications for which people are starting to think that more sophisticated hands will be necessary. And so then the question was, well, what can we do as we build these hands that are able to grasp a wide range of things? And you've seen photographs. This hand can grasp anything from a grape to a large squash, a large pumpkin, so that we can still use the adhesives. And let me hand it over to Wilson at that point.
Yeah, and I think coming at it, it's like that's the implementing the adhesive side of it. And then from the anthropomorphic manipulator side of it, like as Mark had indicated, I kind of have several different hands in the past that did different things and used different contact conditions. But I was always really compelled by this kind of recurrent problem that these anthropomorphic hands in research circles tend to really focus on these complicated grasps with high precision. And they often would kind of lack some of the grasp strength that you need to really exert meaningful forces in the real world and like accomplish useful tasks. And these gecko adhesives are a really nice way to perhaps start to fix that problem in the more anthropomorphic setting, right? Because you have a hand that's inherently not going to be as strong mechanically because there's so many more moving parts and you have worse gearing things going on as a parallel jaw gripper. But you can get more contact area with it because you can kind of mash the hand around whatever shape is, right? And how do you exploit that extra contact area to make a stronger anthropomorphic hand? Well, you use restrictive contact conditions, and in this case, gecko adhesives, right? And so it's kind of a way of approaching this high level problem of how do we have a hand that is dexterous and capable of sophisticated manipulations, and precise, but also strong at the same time. And that kind of marriage just seemed to make a lot of sense. And that's something else that I kind of want to push forward as a general goal of the field.
Mm-hmm. I want to ask you if there's maybe parts in the research, especially in the paper, was maybe hard to explain, or maybe in other sense that you couldn't really have this aspect at the beginning, maybe at the design, and was like, wow, I couldn't get this aspect of design. It wasn't really clear to me. It doesn't make sense. I don't know if you have this kind of part in the paper, how to explain this part, or maybe counterintuitive in the sense of the behavior and how to explain that. Do you have this moments as well, or?
I can point to one point that certainly wasn't obvious to me when we started, although it may have been more obvious to Wilson, which was why we need to have multiple tendons per finger. And the thing is that for 30 some years we've been building hands. We think intuitively about using grasping with Coulomb friction. And so optimizing the grasp is all about controlling normal forces at the contacts, thereby controlling the friction force because, the tangential force is the coefficient of friction times the normal force. That's not true with adhesives. Instead, what you want to do, and this is covered in the paper, and Wilson can explain why, what you really want to do is not optimize normal contact forces, but rather try to make the contacts be along the midpoint of each phalange, thereby maximizing not the friction force, but the contact area.
Yeah, and to go with that, I think to make that happen, you could really carefully design the passive structures of the hand to have the right stiffnesses to get that behavior on certain shapes. But to get that behavior on kind of almost any shape, you need a more highly actuated solution. And there were times when I was designing previous hands where I was working on something, it was stuff where it was typically be like one motor was controlling all 4 fingers or all 3 fingers or something like that. And there were a lot of times where it just felt like, in all honesty, the slightly more complicated solution of having a couple more motors even though the controls are a little bit more complicated, would make so many other elements of that hand so much easier to do that it might actually still be a simpler solution. And I think that's a little bit non-intuitive, that, the lowest hanging fruit isn't always what you think per se.
Mm-hmm. Great. Dan, want to add something here? Yeah, go ahead.
Yeah. One thing I'd like to add is that even just looking at we've talked about these loading principles before, and as you start thinking about like what a pad should look like to try to accomplish these things, you want it to be soft and compliant in normal, but relatively stiff in shear force. And also, hopefully have a certain stress strain profile that can load share and things like that. But even just a simple choice of like, what material do you use? That's immediately at odds with those two goals, right? You can't simultaneously change the material to make it, more compliant in normal, but then softer in shear. And so sometimes decisions like that were somewhat unclear. And I think there were other examples throughout where we had like multiple goals and there wasn't one clear decision. And that's part of, I think, why we recommend this design process of just kind of putting a stake in the ground with the material and proceeding while you consider your design.
That was the extra challenge that Dane. Oops, sorry. Yeah.
Go ahead. Yeah.
I was gonna say, I think, and we've talked about this in a couple other interviews, where it's just that simulating soft structures like this is still just like really difficult to do super well, and we're not an FEA lab per se. And that was kind of on Dane's side of it, was he was working on getting some preliminary results from FEA exploration of it. And it was like we could, and Dane can speak to this more, but what we could do is kind of get a sense for what these super high level structures might do, but really calculating exactly what forces are going to result was really difficult. And that made this whole design iteration loop really challenging. Whereas if these were all rigid structures, you could simulate it much more easily, right? And that just kind of calls for like easily accessible, better tools in that area.
So maybe I want to ask Mark in that point about the coupling of the material, and we have here the material and structure and the control. If you see the three of them, do you think, for example, I think the example of the dead fish swimming upstream and how the coupling of geometric and material nonlinearities can give us interesting behavior, and there is no brain or maybe no control. And there's a tendency in the field to think about the direction. Since you're already using a passive and the Gecko-Inspired adhesion, how do you see the control here? Do you advocate for maybe minimizing the external controller and take advantage of physical intelligence of the passive and the Gecko adhesion material? I'm just curious what are we thinking about these three items: structure, material, and external control?
That's a complicated question. There's a couple of things that one wants to keep in mind. First, control is something that it's relatively easy for us to do at a macroscopic level. We can control the positions of the fingers. We can control the torques that we apply at different joints of the fingers. And that allows us to control the overall pose of the hand, what the forces are, where the contact points are. That's the level where it's straightforward for us to do active control. What makes it complicated is that for Gecko-Inspired Adhesives, there's a lot of the behavior that we need to achieve has important things going on at the microscopic level. So I need to know how the pressure distribution is varying at the scale of a millimeter or less in fact. That's not something that I can actively control. I would need hundreds or thousands of actuators, and so therefore I switch to trying to think about how we can design passive structures that will achieve that desired behavior. Sometimes when I talk about Gecko-Inspired adhesives and I try to explain the problem, like why is it hard to scale this Gecko adhesive to larger tasks or larger applications? I said, well, what you really would like is for every single microstructural fiber of the adhesive to somehow be loaded individually with a tiny, tiny string that would pull on it just as hard as it can withstand and no harder. And then you would gather all these many thousands of strings and you would control them all independently in order to get exactly the desired behavior. The image that comes to mind is Gulliver's Travels, from Tom Swift, where he's held down by the Lilliputians with thousands of tiny silken threads, and each one is very weak, but they're all holding just as much tension as they can, and so he's unable to get up. That's what you would like, but we cannot do that from an active control standpoint. We don't have that kind of degrees of freedom. And that's why we look for, well, are there ways I can approximate the behavior I would like using some combination of elastic structures and materials, to get the effect I want.
I don't know, Wilson and Dane, you would like to add here as well?
Something that comes to mind for me is that another limitation and a potential future work for this work is to get enough information to actually inform how you should control these. So specifically with the structures that we have, it's not super easy to sensorize and have high-level information, especially, as Mark's saying, at this micro scale. There are new innovations like GelSite that, you could maybe envision somehow being incorporated into these ribbed structures that could inform things. But generally, state-of-the-art sensing, even that is a limitation on how well you can control for tasks like this.
I was just saying, there are a lot of really cool tactile sensors out there, and to Mark's point is like you're not going to get that like millimeter by millimeter fidelity with most of them, but are you going to start to get some information about where you're making contact and where you're not? Like, yes, we can start to do that now, and I think that, as Dane pointed out, is that big area of future work to then inform how you use, as we talked about, having more than one tendon. You have this ability to control the angles of your fingers. Now let's use it using these tactile sensors.
What maybe other interesting question or be harder question do you think maybe in the community not handled in a deeper way or deeper discussion? And for yourself, you still don't understand what could be the answer for them?
Well, there are many questions not yet answered, and also, frankly, there are many technological advances that should come along. It's still the case, for example, that these Gecko-Inspired adhesives that we have, they work under a limited range of circumstances. They don't work on surfaces that are wet. They don't work on surfaces that are dirty. And yet, the Gecko does. So there are improvements that should be made there for these hands to be more practical for other applications. People talk to us, for example, about this hand. Well, wouldn't it be great for robots that have to interact with people, helping, the elderly, for example? Well, they would. I think they do help, but they could help more if the materials that we're using actually had an even firmer grip on human skin, despite the fact that it has hair and oil and sweat. So those are some extensions and some unsolved problems that we continue to address.
Mm-hmm. And maybe with the failure, I don't know if in the paper or maybe in the mechanism, how do you see this kind of failure situation or mode, fatigue? I don't know. There's something interesting.
Life is an issue too. Yeah, we don't know actually how well this whole system holds up for weeks or months of use in realistic applications.
Mm-hmm. Mm-hmm. Great. So maybe if we can go to Wilson here about the challenges, maybe limitation in the paper, because sometimes you have limitation and maybe parts still be considered for future work.
Yeah, I think one that jumps out as a little bit of a response to some of Mark's points they just made is that these Gecko adhesives behave very differently based on the different surfaces that you're making contact with, right? And for the same surface, if you have dirt on it, you're also going to get less adhesion. And what we had to do when we were designing the passive buckling behavior of the adhesives was not guess per se, but choose a force zone that kind of encompasses the most materials that we think are of interest and try and get the behavior we want in there. But if you suddenly are interacting with something that's much dirtier, you can drop below the minimum force where it's going to be effective. Or if you're touching something that's perfect glass, you actually are going to kind of underutilize your adhesives because the whole structure will sort of fail before the adhesives do. So we had to choose this zone based on kind of an average of what we were looking at. And I think it would be really awesome to explore ways to expand that range past what it is. And I think it's good to medium now, and I think you could get a lot more. And that also goes to this other question with any, and this is going to be true of any research project like this that comes out of lab, is just like, there's some stuff that are limitations that stem from the fact that it was, two of us building this thing, with not a massive budget, right? So there's a few like things that have to happen there that are lower fidelity than they could be. We have 3D printed plastic parts, and those are always like a little bit of a hazard and whatnot. So some of these problems of robustness are just going to be fixed by bumping up the fidelity of the whole thing, right? You could just throw money at it and those problems go away. But then some of these other problems are things that are just more fundamental research questions, and really teasing out what those are, what are next, I think is the really important parts to kind of moving the whole field forward, at least for us. And that's where I really see the big point we talked about before with, like intelligently adapting tactile sensing into the hand, handling these less obvious, contact scenarios where you're not touching as pristine materials, handling them well, handling them kind of smoothly. And perhaps even from there, starting to handle failure scenarios where even when it doesn't work perfectly, something slips, but can you still adapt and react accordingly?
Dan would like to get something here?
Yeah, I mean, I think Wilson and Mark touched on pretty much everything that comes to mind, but I guess I'll reword kind of a thought that comes to mind based on what they said. But I think something kind of interesting is that we had this goal of creating a general manipulator that could be precise and strong at the same time. And I guess we were very successful on the side of being general for object geometry. So we could grasp a whole range of different sizes and shapes of objects. But as I think specifically Mark was talking about, these gecko adhesives don't necessarily they don't work better than just normal silicone on rougher or wet or dirty surfaces. And so it would be interesting if we could have some sort of adhesive that was also kind of a general adhesive in terms of surface conditions, and then you could have a even broader sense of what a general manipulator could mean, both object geometry and also surface conditions.
Mm-hmm, great. So maybe I want to ask Mark, in that case, since we mentioned limitation, I'm curious to ask you, what does it take that we can achieve, for example, Gecko-Inspired adhesion that can adapt to different surface, whatever, dusty, wet, whatever? What does it take? What do you think the point that we need to push that we can achieve this kind of adhesion that adapt to different situation?
Well, when you look at what's going on with the gecko, I mean, it's an order of magnitude more sophisticated. There are features going all the way down to something like 350 nanometers. We simply are not able to fabricate those structures today and do it in quantities that they're useful for things like hands. But if we did, it would allow us to use stiffer materials. It would allow, and you can show that it would add one more layer of hierarchy in this sort of hierarchy of conformal systems at the centimeter, 100 millimeter, the centimeter, millimeter, 100 micrometer, and now going all the way down to hundreds of nanometers. It would add another layer in that hierarchy and would allow our adhesives to do a better job of conforming to surfaces that are not smooth, for example. Would make it easier for them to clean themselves automatically as you touch dirty surfaces. They should shed dirt, actually. So I think, so where improvements are possible and what we're limited by right now is that we don't have good ways of fabricating more authentic Gecko-like adhesives in quantity.
And maybe for Wilson and Dan, what be other features do you think maybe you wish that you can incorporate in the design? I know that maybe the future work, but maybe features you wish that in the paper.
Yeah, there's another big sensing element that it currently does not have that I really wish it did, which was the ability to directly sense the tendon tension that the hand is feeling. You can sort of approximate that by knowing how much the motor is exerting for forces, but the issue is that that's not always a one-to-one with what the tendon's actually feeling at the fingertip or at different points in the hand. Because if you actuate it closed into a particular position, but then something pushes the object against one set of fingers, your tendon tension will ramp up. But you won't necessarily know that from the motor unless you're actively actuating it and sensing a bunch of other stuff. And even then it's a little sketchy. And that bit of information would allow you to have much better force control over what is happening with those grasps and kind of react more dynamically in force space for what you're trying to do. And I think that in particular is super helpful for these adhesives because the amount of force that you're exerting matters. And one of the high level goals was to grasp gently on some of these more fragile things. So you want to be able to control that as well. And we can sense the position of the fingers and we know how much torque we're exerting through the motors, but we don't know how much force is felt by the tendons. And human beings kind of do have those senses. Like we have some proprioceptive capacity on top of just knowing how much force we're pulling with. I have one more as well, actually. And it's certainly not the easiest or probably best return on investment element to design next, but I still these fingers they only really close through one axis. And when they make contact with something, they will rotate a little bit based on just their passive stiffness. They're relatively compliant, so they'll kind of match shape in this other axis direction. But I wish we could, do add or abduction of the fingers or rotate them. But I think I prefer add and abduction, which is effectively the ability to spread and narrow your fingers out together. If you think about fanning your fingers. And what that'll let you do is control, as we talked about several times, controlling the angle of contact with a surface. It allows you to control the angle in the other direction. And that would dramatically, or not, hypothetically could dramatically improve how much contact area you can get and thereby improve how much you're using the Gecko adhesives. But it's a huge mechanical challenge for the design of the hand, adds a lot of complexity, adds another whole degree of freedom, that you have to control. And then on top of that, you need to know what you want to do. And that comes back to our tactile sensing questions from before. Mm-hmm.
Great. So since it goes to the end, maybe a few questions left. I would like to ask Mark in that case about using the passive and the active material like adhesion here. How do you see the redundancy here? If the passive parts have failure, how do you see the adaptation between, the passive part and the adhesion part and the shape of the design? How do you think about redundancy here?
Well, one thing to be aware of that makes the current application, trying to grasp objects with the hand, very different from climbing a wall, which is where we started. If you're climbing a wall and adhesion fails, you fall. If we're grasping an object and adhesion fails, we're not actually any worse off than we would have been if we just designed an ordinary hand with rubber on the fingers. So in the worst case, it devolves to just being soft rubber with no adhesion, which is actually not all that bad. It's just that you lose the advantages of adhesion where you can use very low grasp forces, hold things very gently.
Mm-hmm. That's an excellent point, yeah. Great. So I don't know if anyone would like to add here something, or Wilson, Dan, it's okay? You want to add something?
I think just a minor point to add on to Mark's there is if you are kind of using these more difficult adhesive grasps, I think there might be some open questions about, can you also choose your grasp selection to be, for a given object and grasp? Can you choose something where if it starts to fail, it will then settle into yet another stable grasp configuration rather than failing catastrophically? And I don't have a great semblance of what that exact answer would be. And I think it's going to be very case by case. But I do think, in terms of Mark's early work on grasp taxonomy, I feel like it could kind of fall into that category of a high level planning going into it that would also give you an added level of redundancy to make the most out of the adhesives as well.
Mm-hmm. Right. So maybe a question about the expectation of the paper and where you want to push more. For this design in particular. If anyone would like to jump in here, what's next?
I think that should maybe get split into two paths, which is what are the remaining research questions, which I think we've talked on several times in terms of the different mechanical changes we might make, the controls questions, and then in particular the integration of tactile sensing. all of those open up a lot of good research questions, as well as Mark's point on having kind of a new layer of hierarchical contact. And I don't know what Dane's plans are, if he plans to pursue more of those things, actually. So maybe he can speak to that. But then the other big branch would be if you were going to maybe make a simpler version and try and commercialize it in a different way, like what are those applications? And I think that's still a very open question that is in large part dictated by some of the stuff that Mark talked about before in terms of handling dirty environments. So we call it farmhand, right? Because it was supposed to pick fruit and do things like that. But doing it 10 times or doing it 100 times is very different from doing it 1,000 times. So then you have these a little bit more commercial questions of how do you make it reliable? How do you make it clean itself? And how do you make it integrate into a full infrastructure for a probably more specialized scenario? And that's something that I think would be really
Mark or Dane, you'd like to hear something for what's next, maybe? Or
Sure.
Yeah.
So I think as Wilson touched on, there are a lot of kind of research questions we have in mind. But I think at least the thing that would be most exciting for me is seeing what steps could be made towards commercialization with something like this. We have been in contact with some people who are interested in working, but kind of no concrete plans yet for what exactly that might look like.
So maybe the question I would like to ask, what makes maybe you satisfied and fulfilled in what you do as a researcher? What makes you satisfied and fulfilled as a researcher?
Well, for me, first of all, this hand is a way to bring to fruition an idea that we've been talking about for quite a few years. As I mentioned, basically ever since we started to work on Gecko-Inspired Adhesives, initially for climbing robots, we had it in our mind that it could be used for other applications as well. And we kind of didn't have all the pieces put together to make that happen. So that is satisfying. It's satisfying to see it work demonstrably well for grasping a wide range of objects very gently with low forces. And, we're always thinking about what will be the next hands that we design. Dane is working with me even now on a new project where we're thinking about robots in the home and what kind of hands will be put on those robots. Sure, if Gecko adhesives will improve the functionality of those hands in some applications, we're happy to make use of them. And I think now we understand exactly what they can and can't do. Mm-hmm. Yeah, I mean, it's eventually it becomes a field like, for example, bicycles. Bicycles have been around for more than 100 years, and yet there's always new and better ones coming out.
Mm-hmm. Great. So also for Wilson, Dan, you would like to say something here, or okay for you?
Yeah, I mean, I think the really satisfying thing that came out of this for me was sort of almost the simple elegance of this buckling rib solution, in that it really just solves like several problems simultaneously in a passive way with a simple structure. And that's like pretty rare to find. And there's a lot of things like most of the effort come into these kinds of things of like getting all the little details right. And that is still, of course, true here, but it was really satisfying to have this like key kind of insight pop out that allows us to get around all these previous problems kind of at the same time if we do it even reasonably well. And like the margins on it, it's like it doesn't even need to be perfectly tuned and still does a pretty good job at what it does. And that always for me is like kind of indicator that it's probably a promising thing, because if you have to get it down to like the 0.0001% perfectly optimized thing just to get it to work at all, then, it's not going to be able to expand to a wider range of circumstances. And we didn't, we had to optimize it some, but we didn't have to go, it could still be somewhat general. And that's really exciting to me.
Mm-hmm. Great. And lastly, Dan, you would like to say something here?
Yeah, I 100% agree with Wilson. I think that's the thing that comes to mind to me most as well. I think generally something that's exciting about soft robotics is this kind of Occam's razor idea, which, it's the simplest solution possible is the best solution. And if you can solve something passively, that's a great accomplishment. And I think we were able to do that pretty well. So that's probably the most exciting, satisfying part for me.
Excellent. So I don't know if you have any final words. Maybe anyone would like to have any final words before we close. Any final words? Maybe Mark, if you have any final words.
One sort of closing thought. I think what we're seeing is the time has come that people are able to build these kinds of hands and actually many other works in soft robotics. And a lot of it really does have to do with innovations in materials and fabrication methods. If I had understood what I needed for farmhand 15 years ago or 20 years ago, I'm not sure that I could have built it. It really makes enormous use of being able to go rapidly from three-dimensional computer-aided designs to 3D printing, either 3D printing directly of parts, or where you can't get the material you want as a 3D printed part, you make a mold and use that to cast the material that you want. It makes a relatively fast process of going from a new idea about how to make it better to a prototype that you can test to see if it's actually working the way you hope it will.